In this video, we're going to look at the interval and radius of convergence of a series. So the first thing, what are they? The interval of convergence is the interval that a series converges on. And the radius, and there's a few ways to find it, but the radius is basically half the length of the interval. Now, how we're going to find this, and we'll see some examples after this, is there will be a variable other than the index variable inside the series. So it's not just going to be like the sum of 1 over n factorial. There's usually going to be an x or some other variable in there as well. And the general method is this. So we will generally use the limit comparison test, which is the limit as n approaches infinity of the following term divided by the current term. And one of two ways. Either I'm going to say that this will be between -1 and 1, and that's the way I'm going to show for example 1. Or I can also show that the limit has a magnitude less than 1. The final thing here is we need to check the endpoints. The limit test only tells me that it definitely converges between -1 and 1. It doesn't tell me whether any of these should have equal to in them. So I need to actually check both the endpoints. That's probably the trickiest part. So let's see a couple of examples. Here's the first one. Find the interval and radius of convergence for the sum as n goes from 1 to infinity of 7x to the n divided by n times 3 to the n. So in here, we'll do the limit test, limit as n approaches infinity of, and I usually like starting, especially for students that are a little bit having a little bit of trouble seeing what's going on, with the nth term, and that's just the general term, that's this. So I have 7x to the n over n times 3 to the n. And on top I should have the n plus first term, so everywhere I see an n, I'll replace it with an n plus 1. So that is going to be 7x to the n plus 1 divided by n plus 1 times 3 to the n plus 1. And all I need to do is sort of work this out. So I need to flip around. There's a few ways to do this. Either I can say, okay, I'm dividing by this fraction, which means I multiply by the reciprocal. This goes to the top, this goes to the bottom. Or I can think of it as exponents, positive and negative exponents. So this is in the numerator of the numerator, positive times positive is positive. Denominator of the numerator, negative times positive is negative. Numerator of the denominator, positive times negative is negative. Denominator of the denominator, negative times negative is negative. Or sorry, negative times negative is positive. So this will be in the numerator, the denominator, the denominator, the numerator. And it'll always work that way. So when I work this out, I'm going to get the limit as n approaches infinity. And if I'm smart about it, I can see things nicely. So I'll put the 7x to the n plus 1. I'll put the n and the 3 to the n. Those are all the things in the numerator. And when I write the things in the denominator, I'll sort of line them up with what they correspond. So the n plus 1 sort of corresponds to the n. The 3 to the n plus 1 corresponds to the 3 to the n. And the 7x to the n corresponds to the 7x to the n plus 1. And working this out, so the limit as n approaches infinity of n over n plus 1 is 1. So for all intents and purposes, this sort of cancels out. I can see that because, so limit as n approaches infinity of n over n plus 1, using L'Hopital's rule, the numerator and denominator both approach infinity. I take the derivative. Derivative of the numerator is 1. Derivative of the denominator is 1, so limit's 1. So it doesn't change my product or quotient here. I have one more 7x in the numerator than I have in the denominator, so I will have a 7x left over in the numerator. I have one more 3 in the denominator than I have in the numerator, so I'll have a 3 in the denominator. And in order for this to converge, I'll say, okay, -1 is less than 7x over 3 is less than 1. Multiply everything through by 3 to get rid of this 3. -3 is less than 7x is less than 3. And divide everything through by 7, and I get that -3/7 is less than x is less than +3/7. Before I go on, this interval is 6/7 long, going left 3/7 and right 3/7, so the radius of convergence is half that. It will be 3/7. The other part, I don't know if it should be equal to on either end, so I have to consider both sides, and that's a little bit tricky. I usually sort of do it at, as I'm working, so let me box it in, that's one of my answers. So at x is equal to -3/7, when I put the -3/7 into my original general term, 7 times -3/7 is -3, so my general term would be -3 to the n over n times 3 to the n. And -3 to the n over 3 to the n is -1 to the n. This is the alternating harmonic series. It converges because of alternating series, so that should be equal. And now I consider the other endpoint, so at x equals 3/7. When I put 3/7 or substitute 3/7 in for x, 7 times 3/7 is 3, so I get 3 to the n over n times 3 to the n. And here the 3 to the n's strictly cancel, I get 1 over n. This is the harmonic sequence, harmonic series. It does not converge, so I do not have an equal to part here. And that is my interval of convergence. -3/7 is less than or equal to x is less than 3/7. That's one way to deal with it, where I sort of split up the -1 and the 1. Here's another way. I could also dive into this problem, so I'll do the limit as n approaches infinity of the absolute value of these terms. So I'll put this all at the bottom. I have, I have n squared times x plus 2 to the n all over 5 to the n in the denominator. And in the numerator, I have n plus 1 squared times x plus 2 to the n plus 1 all over 5 to the n plus 1. And this has to be less than 1. So I've seen some AP free response question grading. They show it like this with an absolute value. And it's the same thing, because if the absolute value is less than 1, then it's between -1 and 1. But this is how they do it. And so I clean it up by putting this in the numerator, this in the denominator, this in the denominator, this in the numerator. So I get the limit as n approaches infinity of the absolute value of n plus 1 squared x plus 2 to the n plus 1 times 5 to the n. And in the denominator, I have a 5 to the n plus 1. That corresponds to the 5 to the n. I have an n squared, which corresponds to the n plus 1 squared. And I have an x plus 2 to the n. And that must be less than 1. And looking at this, just like before, now the n plus 1 squared over n squared approaches 1, so it doesn't change the limit. I have one more x plus 2 in the numerator, so I'll have an x plus 2 left over in the numerator. And I have one more 5 in the denominator, so I'll have a 5 left over in the denominator. And if I do it this way, when I take care of the multiplication in here, I'm just left with sort of an addition, that's going to give me the radius of convergence. So when I multiply both sides by 5, I get the absolute value of x plus 2 is less than 5, and that's the radius of convergence. Radius equals 5. To actually find the interval, I still am going to want to split it up. So let me, interval of convergence, so I will have negative 5 less than x plus 2 less than 5. And subtract 2 from all three sides to get negative 7 less than x less than 3. And now I need to consider the endpoints to see if I have any equal to parts. So at x equals negative 7, when I put negative 7 in here, I get negative 7 plus 2 is negative 5. So I get negative, well, sorry, I still have the n squared. Let me put that in there first. N squared times negative 5 to the n divided by 5 to the n. The negative 5 to the n over 5 to the n gives me negative 1 to the n. But this definitely diverges. The terms don't approach 0. As n is approaching infinity, they get closer and closer to positive and negative infinity. So we don't have an equal to here. And for the same reason, at x equals 3, 3 plus 2 is 5, so my general term is n squared times 5 to the n over 5 to the n. Those cancel. And my general term is n squared. So just think that through. This is the sum, 1 plus 4 plus 9 plus 16. That's not going to converge. Over here, we have, let me see, so when n is 1, we get a negative. So it's going to be negative 1 plus 4 minus 9 plus 16. Neither side converges. So the interval is strictly between those. These first two examples cover a lot of the cases that you're going to see, but there are a couple special cases. So let's see two more special cases. Find the interval and radius of convergence for the sum as n goes from 1 to infinity of x over n factorial. And we dive right in. I'm going to show this the first way. I sort of prefer it. So limit as n approaches infinity of, I have x over n plus 1 factorial divided by x over n factorial. And numerator, denominator, denominator, numerator. So x n factorial over x n plus 1 factorial. And in here we can see the x's cancel. And n factorial over n plus 1 factorial is 1 over n plus 1. I'll explain why in a second. Well, probably 10 seconds. Okay, so as an example, if we had 6 over 7, 6 factorial over 7 factorial, okay? This factorial being 1 more than that, this is 6 times 5 times 4 times 3 times 2 times 1. This is 7 times 6 times 5 times 4 times 3 times 2 times 1. The 6, 5, 4, 3, 2, 1 cancels. I'm left with the 1 extra term. If I had something like 9 factorial over 7 factorial, I can see this will have 2 more terms than that. So I'll have a 9 and an 8, and the 7, 6, 5, 4, 3, 2, 1 will cancel. This has 1 extra term, the n plus 1, and the n down to 1 will cancel. This limit is equal to 0, because as n approaches infinity, the denominator gets larger and larger. And you sort of ask yourself, for what x values is 0 between negative 1 and 1? And the answer is all real numbers. So the interval of convergence for this, because this limit actually goes to 0, is going to be negative infinity is less than x is less than infinity. And the radius is going to be infinitely large. It actually covers all real numbers, because regardless of what real number we put in for x, x over n factorial converges. On the other end of sort of special cases is this. I'll start off with the limit test. So limit as n approaches infinity of n plus 1 x over n x. And in here, the x's, as we saw before, cancel. The limit of n plus 1 over n is going to be 1. And we have to ask ourselves, when is 1 between negative 1 and 1? And the answer is, well, it's never between those. And so in this, almost regardless of what we put in for x, it won't converge. Because just consider, let's say if we put 1 in for x, then this will be 1 plus 2 plus 3 plus 4 plus 5. It's going to diverge. But there is one case where this works. So when things go badly, don't forget that I could have the radius of, or the interval convergence. So the interval is just x equals 0, because 0 is going to collapse down that n and make things work. So we'll get 0 plus 0 plus 0 plus 0, which converges to 0. And the radius is going to be 0 wide, because there's no width to the interval just containing 1.0. So, sorry, containing 1 point, that point being 0, not 1.0 like the number. So in this case, the only thing that makes it converge is x equals 0, and the radius is 0. Comment below if you have any questions, and I hope this helped out.